So we're going to start by talking about the average rate of a reaction. So the average rate, obviously, is the change in something over the change in time because it's a rate in specific. It's a rate. So that's what we're looking at, is the average rate of the change in the concentration of A over the change in time. Now, the change in concentration will be negative. So let's make this a star so that we don't confuse it with a negative sign, okay? The change in concentration will be negative. And here's why. Because what we're doing is we're taking the concentration of A final minus the concentration of A initial. And as we know, when we're looking at a reaction, if it's a reactant, then the initial concentration will be higher than the final concentration. So therefore, the concentration of A will be negative. So I'm going to tell you that we're going to take the negative of that negative to make it positive. And the reason is because we want the reaction rate to always be positive. So, in other words, we don't care about the direction that we're going. All we really care about is how fast it's going. And since it's always headed from reactants to products, it's always positive in that direction. So how fast is this reaction going from reactants to products? It's going at this many molarities per second, moles per liter second. And so this is the units are moles per liter seconds. So this is actually moles per liter second, or molarity per second. All right? All right, so let's look at example 1. So in example 1, you're given this equation. And what we want to do is we want to find the average rate. Am I going too fast? Yes, okay. All right, so we're finding the rate of change. So the rate of change, because of the stoichiometry, is going to be twice that, the rate of the reaction. So I put negative 1 over 2, 2 times the rate, which I plugged in, and then I get negative. And this is negative because it is decreasing. Questions? Okay, let's move on. All right. So, reaction orders. This is where we have been yesterday. Friday, we were looking at reaction orders. So, the equation is first, second, and third, right? So our rate law is rate equals K times A to the N. N is equal to 0. Then the reaction is 0 order. And I'm kind of summing this up because I have been sort of confusing about it. The rate in a 0 order reaction is independent of the concentration of A. And what this means is I can raise and lower the concentration of A, and it will not change the rate of the reaction. N is equal to 1. What this means is the reaction is first order. The rate is directly proportional to the concentration of A. So if I double A, I'm going to double the rate. Two x times A, 2x times the rate. N equals 2, second order. The rate is proportional to the square of the concentration of A. So this is where we say 2 times the square root of A, 4 times the rate. Yeah, 2 times the concentration of A, 4 times the concentration of rate. 4 times the rate. All right, now, the reaction may have fractional order. We've seen that, right? Whether you'll see that on the test, probably not. Most common is 1, 0, 1, and 2. And that's what we're going to focus on. Okay, so we're going to focus on that. Now, graphs. In this unit, one of the questions you will be asked, listen to my wording, will be asked in one way or another. One of the questions that you will be asked if you have one of these questions on rates, if they ask about rates on the test, you will be asked to identify what the order is based on the graph. That's how they will ask it, all right? So there's going to be a few graphs coming your way over the next couple days. Here are the first 2. This is the concentration of A over time. I can. Okay. So we have 3 orders we need to deal with. This is linear for 0 order. Time is in seconds. So this is linear in a 0 order reaction. For first order, this is actually what we call a decay reaction. And for second order, okay? So it looks a little bit weird like that. Now, the next one that we're going to look at is something, and we're going to expand on this, all right? The next one we're going to look at is the molarity per second, which is the rate. Notice the linear function of the 0 order, right? Kind of characteristic when you look at just the concentration of time, right? And the fact that the decay comes down but never actually meets, right? So it's like half by half by half by half, a decay, because it's a half order reaction. Your decay graph is a half order reaction, like a nuclear half reaction. Okay, rate by the concentration of A. So as the concentration of A decreases, what happens to the rate of the reaction? Well, remember, in a zero order, the concentration has no effect on the rate whatsoever. So zero order looks like this. No effect on the rate whatsoever. First order looks like this. As the concentration increases, the rate increases, or this way, as the concentration decreases, the rate decreases. Right? And second order looks like this, exponential. As the concentration increases, the rate increases. Exponential. It's squared, right? So this is the one that we recognize the most, because if we square the concentration, the rate squares. If we, at first order, if we double it, the rate doubles. Zero order, no matter what we do to the rate, nothing happens. Okay? So right away, here is the first of the graphs that you can recognize the order from. So they give you the graph and they say, here's a graph of the rate versus the concentration. You have to identify what order it is. All right? Not so much this one, but we'll talk more about this one because this one's got other implications. So let's finish this off. So the zero order the equation is going to be rate equals K times the concentration of A to the zero, or rate equals K alone. For first order, the rate equals K to the concentration of A to the 1, and then this is going to be a linear graph. And here it is. Linear. And then with the second order, the rate is going to equal K times A, this concentration of A, squared. And so that's going to give you an exponential graph. And here it is, the exponential graph, okay? Okay, so I'm going to modify some of the homework because we didn't get as far as I had hoped. I don't know what I was thinking. Oh, I was thinking, whatever I was thinking. All right, so I'm going to do that right now. All right.
Good afternoon, everybody. Just one event this evening. We do our JV varsity wrestlers the best, and especially our seniors. It is senior night. Tonight at home is a go against Tarpon Springs, 7 o'clock start time. Come out and support your Warriors wrestling team and our seniors. Have a great afternoon.
All right, you guys, have a great day, and I will see you tomorrow. Not much homework tonight, all right? And then because we can't do the next step yet, all right? No, that's not true. 27. So we can do 27. Yeah, 27. 31. 32. 35. Mm-hmm. 36. Yep, I can do that. 37. I can't do 37. Mm. They can do 38.